Dissociation in chemistry and biochemistry is a general process in which molecules separate or split into smaller particles such as atoms, ions or radicals, usually in a reversible manner. For instance, when an acid dissolves in water, a covalent bond between an electronegative atom and a hydrogen atom is broken by heterolytic fission, which gives a proton and a negative ion. Dissociation is the opposite of recombination. Dissociation constant. For reversible dissociations in a chemical equilibrium AB plus B, the dissociation constant Ca is the ratio of dissociated to undissociated compound, where the brackets denote the equilibrium concentrations of the species. Dissociation degree. The dissociation degree is the fraction of original solute molecules that have dissociated. It is usually indicated by the Greek symbol alpha. More accurately, degree of dissociation refers to the amount of solute dissociated into ions or radicals per mole. In case of very strong acids and bases, degree of dissociation will be close to 1. Less powerful acids and bases will have lesser degree of dissociation. There is a simple relationship between this parameter and the Van 't Hoff factor. If the solute substance dissociates into ions, then for instance, for the following dissociation KCl+ Cl-, we would have that salts. The dissociation of salts by solvation in a solution like water means the separation of the anions and cations. The salt can be recovered by evaporation of the solvent. See also. Solubility equilibrium. An electrolyte refers to a substance that contains free ions and can be used as an electrically conductive medium. Most of the solute does not dissociate in a weak electrolyte, whereas in a strong electrolyte a higher ratio of solute dissociates to form free ions. A weak electrolyte is a substance whose solute exists in solution mostly in the form of molecules, with only a small fraction in the form of ions. Simply because a substance does not readily dissolve does not make it a weak electrolyte. Acetic acid and ammonium are good examples. Acetic acid is extremely soluble in water, but most of the compound dissolves into molecules, rendering it a weak electrolyte. Weak bases and weak acids are generally weak electrolytes. In an aqueous solution there will be some CH3COOH and some CH3COO- and H+. A strong electrolyte is a solute that exists in solution completely or nearly completely as ions. Again, the strength of an electrolyte is defined as the percentage of solute that is ions, rather than molecules. The higher the percentage, the stronger the electrolyte. Thus, even if a substance is not very soluble, but does dissociate completely into ions, the substance is defined as a strong electrolyte. Similar logic applies to a weak electrolyte. Strong acids and bases are good examples such as hydrogen chloride and H2SO4. These will all exist as ions in an aqueous medium. Gases. The degree of dissociation in gases is denoted by the symbol alpha, where alpha refers to the percentage of gas molecules which dissociate. Various relationships between Kp and alpha exist depending on the stoichiometry of the equation. The example of dinitrogen tetroxide dissociating to nitrogen dioxide will be taken. N2O4 to NO2 if the initial concentration of dinitrogen tetroxide is 1 mol per liter. This will decrease by alpha at equilibrium, giving, by stoichiometry, 2 alpha moles of NO2. The equilibrium constant is given by the equation, where P represents the partial pressure. Hence, through the definition of partial pressure and using Pt to represent the total pressure and X to represent the mole fraction, the total number of moles at equilibrium is plus, which is equivalent to 1 plus alpha. Thus, substituting the mole fractions with actual values in term of alpha and simplifying this equation is in accordance with Le Chatelier's principle. Kp will remain constant with temperature. The addition of pressure to the system will increase the value of Pt, so alpha must decrease to keep Kp constant. In fact, Increasing the pressure of the equilibrium favors a shift to the left, favoring the formation of dinitrogen tetroxide, hence decreasing the extent of dissociation alpha. Acids in aqueous solution. The reaction of an acid in water solvent is often described as a dissociation, where Ha is a proton acid such as acetic acid, CH3COOH. The double arrow means that this is an equilibrium process, with dissociation and recombination occurring at the same time. This implies that the acid dissociation constant. However, a more accurate description is provided by the Bronsted-Lowry acid-base theory, which specifies that the proton H+ does not exist as such in solution, but is instead accepted by a water molecule to form the hydronium ion H3O+. The reaction is therefore more correctly written as and better described as an ionization or formation of ions. The equilibrium constant is then where is not included, because in dilute solution the solvent is essentially a pure liquid with a thermodynamic activity of 1. Ca is variously named a dissociation constant, an acid ionization constant, an acidity constant, or an ionization constant. It serves as an indicator of the acid strength. Stronger acids have a higher Ca value. Fragmentation. Fragmentation of a molecule can take place by a process of heterolysis or hemolysis. Receptors. Receptors are proteins that bind small ligands. The dissociation constant Kd is used as indicator of the affinity of the ligand to the receptor. The higher the affinity of the ligand for the receptor, the lower the Kd value.